Okay, so on Monday, we talked a little bit about the composition of the atmosphere, that it's dominated by nitrogen and oxygen. But there's also this variable concentration of water vapor that turns out to be really important. Water vapor doesn't last very long in the atmosphere. Its concentration in the air varies a lot over time and over geography. In particular, the important thing is that the ability of air to hold on to water vapor is strongly sensitive to temperature. Warm air can hold much more water vapor than cold air. That's what this curve shows, so that as the temperature goes up from left to right, the ability to hold water vapor goes up very steeply, particularly at warm temperatures. And air is compressible. So at the ground surface of the Earth, there's kind of the weight of all the atmosphere above us pushing down with a total pressure on the order of a kilogram per square centimeter, or in pound units, which you might be more familiar with, about 15 pounds per square inch. Okay, so when you fill up air in your car's tires or your bike tires, you might go up to like 30 pounds per square inch. So that's an additional twice atmospheric pressure, which means that the air in your tires is like 3 times as dense as the air floating around the room. That makes air kind of unusual among all the fluids we've talked about in this class. Most of the other things we've talked about really don't compress very easily. Water and rocks don't compress very easily. Air does. And what that means is, of course, as you go from the ground upwards in the atmosphere, not even that high, 10 kilometers or so, as the pressure gets lower because there's less air on top of you pushing down, air expands, and it expands quite quickly. So that by the time you get up to 10 kilometers or so, the density, the pressure of the air is only a fraction of what it is at the ground. And that turns out to be not just interesting, but it's important because it turns out that if you take air at the surface where it's relatively compressed and you bring it up in elevation and altitude where the pressure is lower, it expands, and when you expand air, its temperature drops. It's an adiabatic process. When air expands, it gets cooler. Okay? And since the amount of water vapor that air can hold is strongly sensitive to the temperature of that air, that means that as air rises, its ability to hold on to water vapor generally drops and may in fact drop below the amount of water vapor that's in it. So if air's got lots of water vapor, but it's cooling down, it's going to reach a point where it can't hold on to it all anymore, and that water vapor is going to start to convert back into a liquid or a solid if it's colder. So you make either clouds or ice crystal clouds, rain and snow eventually. And so to see an idea of how this works, we can imagine, okay, if we have surface temperatures like a warm summer day, 34 degrees Celsius is like 90 degrees Fahrenheit or 86 degrees Fahrenheit. Let's see. Something like that. And let's say that it has about 1.5% water vapor in it, which is, a relative humidity of like 50%. Something like that. As that air rises, it starts to expand. So by the time it's risen to 1,000 meters, 3,000 feet or so, its temperature will have dropped by almost 10 degrees Celsius just because when the air expands, it gets colder. And in fact, in our atmosphere, if you're near the surface, when air rises, its temperature drops by something like 10 degrees Celsius per kilometer. By the time it reaches 2,000 meters, now its temperature's dropped 20 degrees Celsius. And if it still has that 1.4% water in it, it will have expanded somewhat. And so the absolute pressure of water vapor will have gone down somewhat. But nonetheless, its temperature has gone down so far that by the time that parcel of air reaches 2,000 meters or a little bit above 2,000 meters, it's no longer capable of holding onto that water vapor anymore. Some of it has to come out. Okay, so just by taking air near the surface, fairly dry air, only half as much water vapor as it can hold at that temperature, and raising it up a couple thousand meters, its temperature has dropped so far that it can't hold onto that water vapor anymore, and it starts to condense out as a cloud. Now in the real atmosphere, it's a little bit more complicated than this. You can supercool air. You can actually get a little bit colder than it technically is able to hold onto the water vapor before clouds start to form. It takes some time. It takes some nuclei. But this basic idea that where air rises, it loses its ability to hold on to water vapor and tends to condense out water to make clouds and eventually precipitation holds across the planet. Okay, so places where air is rising are places where condensation, clouds, precipitation, snow are likely to happen. What's going to happen in the reverse process? What happens if you have air aloft and you bring it down to the surface? You're compressing it. So what would you expect to happen to its temperature? Yeah, it should warm up. And you've probably all had experience with this, although you may not have noticed it as such. If you pump up a bike tire, or you go to the gas station and fill up your car's tire, the tire actually gets warm. Okay, the valve on the tire might even get hot to the touch because of all the air that's being compressed. Okay, so here's another relatively prosaic example to show you that when air expands, its temperature drops and it may start to condense out clouds. You can actually make clouds of your own. So what we have here is a bottle of, oh boy, I think this is real Coke, not Diet Coke, but I'm not totally sure about that. But I think the red cap means it's real Coke. Okay, so we have Coke that just came out of the Coke machine. It's under pressure because of all the CO2 that's dissolved in it. And when you open the cap and let that pressure go out, the air temperature inside drops because the pressure is dropping, the air is expanding. So much so, in fact, that water vapor comes out and forms a little cloud in the top of the Coke bottle. Okay, you can see that one more time, hopefully. This time it will work again. Okay. So we have air that's been sitting over this water-rich fluid. It's got as much as it can hold. And then when you release the pressure, the temperature drops and it condenses out and you make a little cloud. Okay? And I'm sure you've seen this. When you open up a can of soda or something, you sometimes see a little cloud of vapor come out. It's pretty common, in fact, in many occasions where you decompress air. Yeah. All right. So are there any questions about this idea that air expanding tends to cause condensation of liquid or solid water? It's going to be really important. Because if we go back to that picture of the hurricanes, okay, what's really going on there, by and large, is that all those places you saw clouds, those are places where air is rising, and thus losing its ability to hold on to water vapor. Okay, so what you're tracking when you look at clouds on a weather map or something, a satellite picture, it's actually, you're seeing the parts of the Earth where air is rising high enough that it loses its ability to hold on to all the water vapor that's in it. So next question, of course, is, okay, why is air rising in some places and not others, right? Why isn't the Earth uniformly covered by clouds, or why are there clouds at all? Why is there vertical mixing in the atmosphere? In particular, why is air rising? So we have to think a little bit about where energy might come from that can drive mixing. And for the most part, not counting, the picture of the fire I showed you on Monday, where energy was coming from the burning of wood and driving convection. In general, on the Earth, the energy that drives vertical mixing and thus the formation of clouds and the winds that blow across the surface of the ocean and drive surface currents comes from solar heating. It comes from the sun. So the basic idea is that the Earth is, at least on the half facing the sun, receiving that solar energy. And that solar energy heats up the surface of the Earth. The energy is absorbed in the atmosphere. Some of it bounces right back into space, and some of it's absorbed at the bottom of the atmosphere where the sunlight hits either the land or the ocean. Okay, so the amount of energy that's deposited at the surface of the Earth is going to depend on a lot of things. It's going to depend on the angle of the sun. If the sun is straight overhead, it's going to be shining most intently relative to the ground surface. If it's very low on the horizon, it's not going to be shining as intently per square meter of ground surface. It's going to depend on the reflectivity of the surface. Okay, if you have something that's dark colored, like an asphalt parking lot, that's very good at absorbing sunlight energy, so it's going to tend to absorb more heat. If you have something that's light colored, okay, like a white painted roof, for instance, it's going to reflect a lot of that sunlight energy right back out into space, and it's not going to absorb heat as efficiently. And of course, the atmosphere itself plays a role. If there are things like clouds in the way or smoke or other particles, then the sunlight won't tend to make it all the way to the ground. It will either bounce off of the cloud back into space or be absorbed within the atmosphere itself. So one of these things in particular we're going to have to pay some attention to understand why winds blow the way they do, and that has to do with the angle of the sun. So let's look at that in a little bit more detail. Okay, so this is a little graphic that shows a picture of the Earth. And you're supposed to imagine that the sun is over here somewhere, way off in the distance, because it's pretty far away. And these little yellow lines that are parallel to each other, that's sort of the direction that the sun's rays are coming to hit the Earth. Okay? And so here's the equator, Here's 30 degrees north, here's 60 degrees north, and there's the North Pole. Okay, so let's imagine that we have, this little red slider, which represents an area on the Earth's surface. If we put that right near the equator, here you can see it's intercepting 1, 2, 3, 4, 5, 6, 7, 8 lines because it's oriented perpendicular to the direction of the sun's rays. So you can say that's the most intense possible receipt of sun energy, all things being equal, like the reflectivity of the ground and all that stuff. If we move that bar farther up, let's say up near 60 degrees or so, okay, at this point you can see instead of intercepting 8 lines, it's intercepting 1, 2, 3, 4, maybe 5. Actually, technically at 60 degrees it should only be intercepting 4, but it's a cartoon, I guess. So at this latitude, the intensity of sunlight per area on the Earth's surface is only half as great as it was down near the equator. Okay, so the rate at which the surface is going to heat up, all else being equal, is only about half as large by the time you get up to 60 degrees north as it was at the equator. So which would you expect to be warmer? Yeah, the equator, right? It's being heated most intensely. And of course, if you take it to the extreme, if you go all the way up to the pole, right? Maybe you're only intercepting 1 line, and it turns out there are some complications. For part of the year, there's no sunlight at all at the pole, and for part of the year, there's weak sunlight. But it's never as intense as it is at the equator. Okay. So let's hope it behaves for the rest of the hour. Okay, so we can actually make a funky graph of that property, the fact that sunlight is absorbed most intensely or falls on the Earth most intensely near the equator and less so near the poles. And so what's being shown here is in units of watts, which is the metric unit for energy per unit time, watts per square meter. So the amount of energy on average per second per square meter falling on the Earth's surface. Okay, and actually this is not for the surface, this is actually for the top of the atmosphere. So we're ignoring possible problems with clouds and whether you have an asphalt parking lot or a really bright snow field, for instance, that reflects lots of the light to space. You can see there's a very simple relationship, lots of intense sunlight hitting the Earth, or at least the upper atmosphere of the Earth near the equator, and becoming much weaker as you go to the poles, varying from something like 400 watts per square meter on average, which is like 4 light bulbs per each square meter. That's actually pretty strong, to very close to half that or less when you get near the poles. Okay, if we take account of the fact that, of course, the Earth isn't uniform, some places have lots of clouds that reflect some of that energy back to space. Some places are darker than others, like Antarctica is mostly covered by ice, which is very bright colored, so it reflects a lot of the sunlight that hits it back into space. Then we end up with a map that looks something like this, okay, which hopefully is similar to this one to your eye, right? We have these kind of reddish colors, at least near the equator for the most part, and particularly dark colored areas like the Sahara Desert. Not quite as high as 400 watts per square meter, but 300 or so. And then as you go towards the poles, the amount of energy that reaches the Earth's surface and gets absorbed gets much, much smaller. Okay, so the Earth is heated by the sun much more intently near the equator than near the poles. I'm kind of belaboring this point, which may seem obvious to you, right? The equator is a hot place, the poles are a cold place. But it's actually important for a couple reasons. First of all, we're setting up a temperature gradient across the Earth's surface here, an energy gradient, right? And we found that things like vertical mixing, convection happen where you have temperatures that are different in one place than another. But we can even say more about that process, because if you look at the variation in the amount of heat that's reaching the Earth's surface, and then you compare that to the temperature, there's actually kind of a difference. The variation here is really big, sort of an order of magnitude, okay, factor of 10. But temperatures don't vary by as much as you would expect, were that the case. We'll come back to that in a minute. There's one other complication here. In the picture I showed you, and in these things, these two pictures, which are sort of annual averages, we're ignoring seasons. And of course, we know that temperature, the amount of sunlight we get varies depending on what time of year it is. So we'll make a little diversion to talk about the seasons a little bit Again, this is something that's probably a review for most of you, but it's worth just getting us all on the same page. Okay, so when I made this, it was October 26th. Of course, it's not anymore. Now it's the 28th, I think. And that puts us right about here in the Earth's orbit around the sun, not drawn to scale. We're somewhere between the equinox, which was September 22nd, and the winter solstice, which is coming up in the end of December, a little bit after finals week. And what we're seeing here is the fact that the Earth's spin axis is tilted somewhat with respect to the direction from the Earth to the sun as we go around in our orbit. And in particular, in a couple of months, at the end of December, we'll be in a configuration where the Earth's spin axis is pointed something like 23.5 degrees directly away from the sun. Okay? The North Pole will be in the Earth's shadow by something like 23 degrees. And so the northern hemisphere of the Earth, which is pointing away from the sun, will, over the next several months, be getting less sunlight energy than the southern hemisphere. Okay? The South Pole is kind of pointed towards the sun now, so it's actually south polar spring coming into summer, and they're getting extra sunlight energy. So in addition to this observation that there's more intense sunlight heating at the equator than at the poles, particularly when you get close to the poles, there's a wide variation in the amount of heat depending on what season it is, how the Earth's rotation axis is pointed relative to the sun. Now, as the Earth goes around the sun a quarter of the way towards the end of March, at that point, the Earth's spin axis will be such that it's kind of oblong towards the sun, so that both poles are getting the same amount of sunlight. And then 3 months later, we'll be on the opposite side from where we were at the winter solstice. We'll be at the summer solstice for the northern hemisphere, when the North Pole is actually facing towards the sun by 23.5 degrees. So that the northern hemisphere at this point is actually receiving extra sunlight, extra heat energy. And then back around, and back to where we are when I teach this in 2010. Okay, so we have to pay some attention to that, right? That the heating of the Earth depends on latitude. It's most intense near the equator. It depends on, of course, to some extent on what the surface is made out of and how many clouds and stuff there are. And it depends on the season. When the North Pole is pointed away from the sun, there's not going to be very much solar heating there at all. When the North Pole is pointed towards the sun, there's going to be relatively greater heating in the northern hemisphere. So we kind of put that together, okay, we can figure out, okay, how much sunlight's coming in from the sun, and it turns out that we can actually measure how much energy is being radiated from the Earth back out to space. We're this big globe of a planet that's floating around in a much bigger vacuum of space, and that's where sunlight energy eventually goes, most of it. It gets radiated right back out into space, which is much colder, of course, than the Earth is. Okay, so we get energy from the sun, and we radiate that energy back out to space. And what we can do by flying satellites, for instance, that look down and figure out how much energy is coming off the Earth's surface, is we can calculate a balance. How much energy is coming in from sunshine, and how much energy is coming out by radiation from the Earth's surface. And we can make a balance and see, are some parts of the Earth getting more sunlight energy than they give off in radiation? Are some parts of the Earth giving off more radiation than they're receiving from the sun? Okay. And if those two things don't quite balance, then there must be heat getting moved around some other way, which turns out to be mostly by wind, but also to a certain extent by ocean. Okay, let's see if this one actually works. Please work. Okay, there we go. Okay, so this is just such a calculation over 3 years from 2006 to 2009 of the heat balance of the Earth's surface. And the reddish colors and the yellowish colors indicate parts of the Earth's surface that are receiving more sunlight energy than they are radiating off to space. And the bluish and greenish colors, like you see down here over Antarctica, are indicating these are areas that are actually radiating more energy off to space than they receive from the sun. Well, you can't do that forever, right? Unless heat's coming from somewhere. So what we see from a figure like this is that accounting for the fact that the deposition of solar energy depends on what season it is, it moves up and down with the seasons, up in northern hemisphere summer, down in southern hemisphere summer, and back and forth one cycle per year. In general, areas near the equator are net receivers of solar energy. They get more solar energy than they radiate away. So some of the extra heat must be going somewhere. And the areas near the poles are in general in a net deficit for energy. They don't receive as much sunlight energy as they radiate off to space. Okay? So there's extra energy coming in here, and there's extra energy going out here. So heat must be getting transported by some other way than by radiation. So what's going on? What's heat doing in the system? If there's extra heat coming in at the equator and extra heat going out at the poles, what must be going on near the Earth's surface? Yeah, there has to be heat transfer from the equator towards the poles. And that's happening basically from two processes. It's happening in the atmosphere by winds that get heated up near the equator and move towards the poles, carrying that heat with them. And to some extent, it's being carried by ocean currents, which also get warmed up near the surface of the ocean, near the equator, and carry that warm water to the poles. And then cold water from the poles is somehow coming back to the equator to get heated up again. Okay? So the fluids at the Earth's surface, the atmosphere and the ocean, are actually really important for transporting heat. And it's a lot of heat. Okay? These orangish colors are implying transfers of energy on the order of 100 watts per square meter, or something like that. So it's like a light bulb's worth of energy being ferried for every square meter from somewhere near the equator towards the poles. A lot of energy. Okay? If you average all the square meters on the Earth's surface, that's a lot of light bulbs. So how is this working? Well, it's fairly prosaic, actually, in its gross properties. Think of a room with a radiator and a cold window. The radiator, for hot water or steam or whatever its source of heat is, heats up the air around it. That's what it's designed to do. When air warms up, it expands, becomes less dense, and tends to rise. So the air piles up at the top of the room over the radiator and spreads out. And eventually it spreads out to the side of the room where the window is, where some of that heat energy gets radiated away to the much colder outside. As the air cools down, it radiates off its energy, it becomes more dense and sinks down to the floor and returns along the floor back to the radiator. So here we're seeing a system where heat is being transported by convection. Warm air is rising and moving towards the cold side of the room, where it cools down, sinks, and returns back to the radiator again. Okay? So we can think of the Earth to first order, with some simplifications, as being like a room with a radiator and a window, where the radiator is the equator, the part of the Earth that receives the most sunlight energy, most intense sunlight energy, and the poles being the part that receives the least sunlight energy. And convection transfers heat from the equator to the poles, okay, both in the atmosphere and in the ocean. So we're going to focus on the atmospheric part. Okay. So the analogy would be something like this. We have our globe, we have the equator, where the heating is most intense from sunlight, and so air is going to be getting hot there. It's going to tend to become less dense. It's going to rise and flow out at some altitude. When it gets up near the poles and the north and south poles, it becomes cold, it becomes more dense, it sinks, and it flows along the surface of the Earth back to the equator. Okay. If this were true, sitting here in Southern California, which direction would the wind blow? Who says it would blow from the north towards the south? All right, some hands. Who says it would blow from the west towards the east? South towards the north? A few hands. East towards the west? All right. Seems like the majority has it. The air is sinking, since we're in the northern hemisphere near the North Pole, and is returning to the equator along the surface. So in California, we would expect to see a wind blowing from the North Pole towards the equator, a wind from the north towards the south. To make you as confused as possible, we name winds after where they come from. So in this simple picture, we would expect California to have northerly winds. Okay, the wind would blow from the north most of the time. But of course, that's not actually what happens in California. We occasionally get winds from the north, particularly on Santa Ana days, but that's not our usual state of affairs. A nice cool day like today, that's not what's happening. At least I'm pretty sure that's not what's happening. Okay? But the first order, this is actually, there's a lot of important stuff here. It is true that the most intense heating occurs at the equator, and you would expect air to be rising there. And you would expect air to be cooling near the poles and sinking there. And those are both true. Okay? It's what's happening in between that turns out to be more complicated, and it's more complicated because the Earth is spinning, as it turns out. So here's a picture, a cartoon really, of what the actual atmospheric circulation looks like. And it's more complicated than the picture in the previous slide. But there's some similarities. There is air rising at the equator in this picture, and there is air actually sinking at the poles in this picture also. So those are both holding up. But there's not one convection cell in each hemisphere, right? It doesn't rise at the equator and go all the way to the poles and then come back all the way on the surface, which actually divvied up into 3 bands per hemisphere. It's more complicated. So to understand why that happens, we have to understand what happens to things that are trying to move on a spinning body, because our Earth spins once per day on its axis. That amounts to a speed for us at the surface of the Earth of hundreds of miles per hour, okay, of order 1,000 kilometers per hour or a little bit more. It's pretty fast, actually, how fast we're moving as the Earth spins on its axis. And that's enough to actually really strongly affect any kind of flow that's moving across the Earth's surface that isn't strongly coupled, that isn't bound to the solid parts of the Earth. Okay, and the wind is a vaporous thing. It's not actually very strongly bound to the surface, and so it turns out to really care about the Earth's rotation. And this idea that things get kind of funny when you have things that are flowing or moving on a spinning body is called the Coriolis effect, okay, or it's a consequence of the Coriolis effect. And so I'm going to show you a few little movies to give you a sense of the weirdness that happens when you go from a fixed at-rest reference frame to a spinning reference frame, bearing in mind that we are standing on a spinning body, so our reference frame is spinning once per day. Okay? So these are movies that are actually made at UCLA in John Arnold's lab. Rob Hyde there helped put a lot of these together. And the basic setup here is basically a record player, okay, a turntable, but instead of having a record on it, we have a little tank or box, and attached to the record player we have a camera pointed down. So if you turn on the turntable, it starts to spin right at 33 rotations per minute or something like that, of order a half a rotation per second. And we can actually mount a camera in such a way that it's spinning at exactly the same rate that the tank is, or the box is spinning. So we can both look down without being attached to the turntable and see it spinning, and we can spin with the turntable. Okay, and on Earth, we would imagine that the Earth's surface is like the turntable. Okay, and our position as beings that are standing on the surface is that we're attached to the turntable. We're spinning with the planet. Okay? So, the first picture, the first movie, is from the perspective of a fixed reference frame. We're not spinning with a turntable here. We're just standing in the room. Okay? And in this case, we have a very simple setup. So, little box on the turntable. We're just rolling a ball across the turntable. Okay? And, well, what's the ball do? It goes in a straight line, right? When you give something a push, it goes in a straight line unless some force acts against it. Okay? In this case, it's just a flat piece of paper on the turntable, so the ball just rolls right across in a straight line. Okay? Nothing really strange here at all, right? But what happens if we consider the same thing, the exact same event, a ball rolling in a straight line across this turntable, from the reference frame of the spinning turntable? Okay, so now we're going to go into the point of view of a camera attached to the spinning disk. Okay, so now we're looking down from above onto this flat piece of paper. And here's the ball rolling across it. Now we just showed, right, you just saw that from the perspective of somebody standing in the room, not spinning with a turntable, this ball is going in a straight line from one side to the other. But that doesn't look like a straight line. I hope everybody can see that. Right? The ball is actually looking like it's going in kind of a circle, at least until it hits the edge. And then it makes another little circle, actually. Okay. So this ball is going in a straight line, but from the perspective of something that's spinning, from the spinning point of view, it looks like the ball is curved. Its path is curved. And in this particular case, because of the direction that the turntable is spinning, it's bending to the right? It's kind of making a clockwise pattern. But you can imagine if we took the turntable and we spun it the other way. Okay. Again, this is a ball that's going in a straight line. Okay, we just reversed the direction of the turntable, and now it appears that the ball is going in a left-hand circle, in a counterclockwise circle. Okay. So, in reality, things tend to go in straight lines unless some force is acting to remove them from that straight line path. Okay, they have inertia, they want to just go in the direction they're going unless something pushes them out of the way. But from the perspective of somebody that's already spinning, a straight line is going to look like a circle or like a curved path. This is kind of a classic movie, although I couldn't quite figure out where it comes from. And it's the same idea. So we have kids playing with a ball on a merry-go-round. Okay? And for the perspective of the merry-go-round, it looks like that ball is going in a really crazy, curvy path. But if you look at it from above, it looks like everything's perfectly normal. The ball is going in a straight line. Nothing strange is happening. I'll do that one more time. Okay? The yellow ball looks like it's going in a straight line here, hopefully. But from the perspective of the kids on the merry-go-round, okay, that ball is acting really weird. Okay. Trust me, those balls are actually going in straight lines, or pretty close. Okay, so what does this mean for us as denizens of a spinning planet? Okay, what this means is that because the Earth is spinning on its axis once per day, something like a wind or an ocean current or like an artillery shell, okay, something that's out of contact with the solid Earth, that's just trying to go in a straight line, okay, is actually going to appear to follow a curved path. Okay, from the perspective of geography, fixed to the surface of the Earth as it spins, these things will go in curved lines, okay, even though they're trying to go straight. And the direction of the curvature depends on which hemisphere you're in. In the northern hemisphere, something that's trying to go in a straight line will appear to be deflected towards the right. In the southern hemisphere, the same thing trying to go in a straight line will appear to be deflected towards the left. All right. Let's see if I can spend a minute and make that make a little more sense. Imagine we have a cannon set up somewhere near the equator, and we shoot a cannon bullet towards the North Pole. Okay? Pow. Okay, and our cannon bullet comes out. Okay, what's going to happen to that cannon bullet? Well, it's heading north, okay? But at the same time, the Earth is spinning on its axis, and it's spinning this way, right? On its axis, the Earth spins that way so that sunrise happens first on the east coast and then on the west coast. So the east coast is first, then the west coast. We're going that way. Okay. As this bullet travels towards the north, it's traveling from a part of the Earth that's pretty far away from the Earth's spin axis towards the North Pole, which sits on the spin axis itself, right? And so the speed at which that surface is going is relatively large when you're near the equator because you're far away from the spin axis and you have to go all the way around it once per day. So you're going at like 1,000 kilometers per hour or 1,500 kilometers per hour. But by the time you get to the North Pole, the speed is zero. You're standing on the spin axis, all you're doing is doing this, okay? You're not actually moving at any speed, you're just spinning. Okay? So as this travels north, okay, it's also when it starts traveling with the surface of the Earth. And when it gets up here, the surface is actually not quite going as fast. Okay. When it was launched, it was going fast. The surface of the Earth, when it gets up here, isn't going as fast. The cannon bullet has both the power that you put into it by burning off the gunpowder and shooting it, and this velocity that came with the fact that it started near the equator. So relative to the Earth's surface, it's going to appear to start drifting off that way because there's extra sideways velocity relative to the ground that it's flying over. It started off way away from the equator, moving from west to east really fast. Now it's over a part of the planet that's not moving as fast from west to east. And so it's going to appear to be going from west to east. It has extra west-east velocity. Okay, so instead of flying straight up to the pole, okay, this bullet actually is going to drift off to the right. And in fact, if you were an artillery captain and you had to direct your battleship to shoot a bullet 28 miles or something like that to hit the shore batteries, and you didn't make this correction, you would miss. Okay? It becomes important, actually. All right? So that bullet's going to trend towards the right, and anything, a wind is going to behave the same way. Moves from south to north in the northern hemisphere, it's going to go towards the right. And it turns out it doesn't actually matter which direction it goes. If you set up a cannon here, okay, and shot towards the south, here it's starting off at a part of the planet that's going kind of slow. By the time it gets down here, it's going over a part of the planet that's spinning fast. It's not going as fast because it started out up here, and so its path is going to tend to go off this way. It's going to lag behind the surface of the Earth from the perspective of somebody standing on the Earth's surface. And so again, it's drifting off towards the right. Okay? Shot to the north, it goes to the right. Shot to the south, it goes to the right. Actually, shot towards the east, it goes towards the right. Shot towards the west, it goes towards the right. It doesn't matter which direction you shoot it. If you're in the northern hemisphere, that bullet's heading off towards the right. Southern hemisphere, it turns out to go the other way. Okay. This one starts out with all this extra velocity. By the time it's over this part of the planet, the surface is going much slower. So it has all this extra velocity relative to somebody at the surface. It's going to appear to be going overhead. It's going to appear to be spinning too fast. Okay? And in that case, what direction does it appear to be bending? Left. Up here it was to the right, down here it's to the left. All right? So something that's trying to go in a straight line, unless something's pushing it, in the northern hemisphere from the perspective of somebody standing on the Earth's surface, is going to appear to be curving towards the right. In the southern hemisphere, same idea, but it's going to tend to be curving towards the left. It's going to appear to be curving towards the left. Okay, in the context of wind, if we have air rising at the equator and trying to make it up to the North Pole, what's going to happen to that wind? It's too far away from the Earth's surface to feel much pull by the surface, so it's just like a cannon bullet. So what's going to happen to a wind that starts out at the equator, rises, and tries to make it up to the North Pole? It's going to get bent. In which direction? So which way is it going to end up going? It's going to not be going from south to north. It's going to be going from southwest to northeast or something like that, and eventually towards the east. So what would you call that wind? We name winds after where they come from. We call it like a southwesterly, right? What about the wind at the surface, which of course is the winds we really care about because we live at the surface and the ocean is at the surface. So if you have a wind that's trying to go from the North Pole towards the equator, but it's getting bent towards the right. So what direction does it end up going? It ends up going from east to west, right? So what do we call that wind? We call it an easterly or a northeasterly, right? Because it's trying to get from north to south, but it's getting bent so that it goes from east to west. Right. So that turns out to be the reason why, instead of having one simple convection cell per hemisphere and winds always blowing from the north in California, we actually usually have winds that are blowing from the west. So a couple more details about this idea of bending caused by the fact that we're on a spinning planet. That the strength of that deflection actually depends on where you are. Okay, it goes from towards the right in the northern hemisphere to left in the southern hemisphere. So you can imagine there's got to be some transition between them, right? And it turns out that as you get close to the equator, to the boundary between the two hemispheres, the strength of the Coriolis effect goes to 0. Okay, so it goes from right near the North Pole, weaker and weaker and weaker, to 0 at the equator, and then stronger and stronger left as you go south of the equator towards the South Pole. Okay, so it depends to some extent on latitude. Coriolis effects are weakest at the equator, strongest near the poles. Okay? And you could imagine, okay, Earth not being the only planet, okay, that if a planet was rotating really fast, if the surface had a really strong velocity, then these Coriolis effects might get really intense, right? Because there's all this extra sideways velocity working around the system. And likewise, if the planet's really big, then when you're sort of at a given latitude, you're much farther away from the spin axis, and so in order to get around once per rotation, you have to be moving much faster. So you can imagine that in a planet that was spinning faster than the Earth and was much larger than the Earth, Coriolis effects would be even bigger. Anybody think of a planet where that might be the case? What's a bigger planet than the Earth? Jupiter. Does anybody know how fast Jupiter spins? It's about once every 10 hours. Okay, so a Jovian day is actually less than half as long as an Earth day. And Jupiter, the planet, is much, much bigger than the Earth. So Coriolis effects on Jupiter are way bigger than they are on Earth. Okay, and instead of having 3 wind bands per hemisphere, it turns out that Jupiter has lots of wind bands. There's more complications to it than that. Okay, and you can imagine if you had a small planet that didn't rotate very fast, it would not have as strong a Coriolis effect as the Earth. All right. So here's something to think about for Friday. I just told you that things bend to the right in the northern hemisphere and things bend to the left in the southern hemisphere. Here's a picture of a really prominent atmospheric circulation feature in the northern hemisphere, a hurricane. Here's Puerto Rico for scale. Okay, it's big. Here's a hurricane in the southern hemisphere. Which way is stuff bending up here? Is it bending towards the right? This thing is rotating counterclockwise. It's going like this. Okay. Remember the right-handed Coriolis effect I showed you in the video? Things are going the other way. How about in the southern hemisphere, where things usually go towards the left? This thing is actually spinning clockwise. Okay, so when we come back on Friday, we'll explain, hopefully, why these things appear to be going backwards. It actually makes sense, I assure you. And we'll get to that at the beginning of the lecture on Friday.